Hi everyone. So today we're going to talk about how light bends and bounces when it goes into a mirror or when it goes through a piece of glass and so on. Here are the learning objectives as always. Feel free to look at them if you want, otherwise let's just move on with the video. So before we start talking about refraction, reflection and all this kind of stuff, the first thing that we need to consider is what is light? So of course we're doing waves, so you may have guessed that light is a wave. But a wave of what? So remember that in sound, you needed some kind of material to transmit the sound, right? Because you had a bunch of molecules, right? And they were pushing each other, and then because it's this push that gets transmitted, and therefore you get a sound. So in vacuum, for example, you get no sound because there's no molecules to push each other. So light is obviously different because we're getting light from the sun, but there's a huge vacuum between the sun and us, right? So here's the sun, and here's the earth, and light obviously gets from here to here, but how? Because there is nothing in here to transmit light. But it turns out that light is the only wave that can travel through vacuum, well, barring gravitational waves, but we'll talk about that some other time. And how does it do it? What is oscillating up and down? What is being transmitted? And it turns out that the answer is a little bit abstract. The answer is an electric field. You probably have never heard about electric fields, so I'm just going to briefly explain to you what an electric field is. Remember that there's two types of charges, right? Plus charges, minus charges. And when we have two charges next to each other, they repel, right? So this guy will tend to go this way, this guy will tend to go this way. So there's something that's transmitting a force from here to here. And we call this thing an electric field. It's like a little web that this guy establishes all around itself. And then when you put some other guy in the web, then it immediately feels the force. And we will talk about this in much more depth when we do electricity. Now, if I move this guy back and forth, this guy is also going to feel a force that goes back and forth, right? So somehow, the movement of this guy is being transmitted inside the field. And it turns out that it takes, that this perturbation in the field travels exactly at the speed of light. Because it is light. Light is basically made of oscillation of this electric field, this web that this guy is making around itself. So every time that I make a charge go up and down, the perturbation in the electric field will be a wave, and that's what light is made of. Just, a little perturbation in the electric field. This usually happens when there's lots of charges moving around. So in the sun, things are very hot. There's lots of charges moving around. Because they move around so fast, they create these really energetic waves that propagate in the electric field, and then they reach Earth, and we call them light. And that's why this can propagate through vacuum, because the electric field exists in vacuum, and therefore waves can propagate in it. Okay, so now that we know this, a couple of things that we need to know. First thing, the speed of light. You may know this already, but the speed of light, which we normally write as c, is 3 times 10 to the 8 meters per second, or 300,000 kilometers per second. And that's very fast. It's so fast that actually nothing in the universe can move faster than this. This is the maximum speed in the universe. And if you want to know why, you need to do a little bit of relativity, and you will do that during the IB diploma, if you do it with me. So this is the speed of light. But however, there's different types of light, right? Because I can have light with a very big wavelength, right? Like the equivalent to a low-pitch sound, but with light. And I could also have light with a very small wavelength, right? But it turns out that it doesn't matter what the wavelength is, the speed of light is always the same. So all types of light travel at the same speed. Now the second thing that we need to know is that different wavelengths correspond to different colors. So when you say you're seeing red, what you're really seeing is light of a certain wavelength that then gets absorbed by your eye, and then your eye goes like, oh, red. Right? So for example, here's your eye, here's some light coming in, then there's a nervous impulse that goes through your brain, and then your brain says, oh, red. And then if you get light of a different wavelength, let's say that this one's smaller, again, this creates an impulse that goes to your brain, and let's say that your brain says, whoa, blue. So really, the universe has no color. The colors are really made up by our brain, just by interpreting different wavelengths that are coming to the eye. Because we have different cells, each one is sensitive to a different wavelength. That's pretty much it. And what's more, we don't even see all the wavelengths there are. We just see a very limited range of wavelengths. Let me show you. Alright, so here you got an image that I got from Wikipedia, showing the different wavelengths of light and their properties. So it turns out that this region here, this is what we can see. We go from red to purple. Everything outside this tiny region here, we cannot see. Now, waves this way have more energy. So ultraviolet has more energy than visible light because it's beyond violet, that's why it's called ultraviolet. And it's what gets us a ton, and it can also get you a skin cancer. That's why it's a little bit dangerous to stay in the sun for long. You get lots of ultraviolet rays when you're in the beach, for example. Then we have X-rays, which, as you know, are used, for example, to look at your bones inside and go right through your body. These ones have even more energy than ultraviolet light. And finally, we have gamma rays, which are produced in high energy events in the universe, and then when they come to the Earth, they're extremely dangerous. But normally they don't really get through the atmosphere, and when they do, there's very, very few. So, nothing to worry about. When there's radioactivity, there's lots of gamma ray produced, and then you may have a problem. And then on the other side of the spectrum, we have infrared. And infrared is radiation that's related to heat. So when you are in a place that gives us a lot of infrared radiation, you tend to absorb that radiation, and that makes you feel hot. Of course, things that are very, very hot actually give, radiation here. But most things that are hot in the range that we're used to give off infrared radiation because it's more or less the size of our atom, so it can easily be absorbed by us. The atom, a molecule, something like that. Okay. Then we've got microwaves, which you know what they're used for. They're used for microwave ovens, of course, and they have even longer wavelengths. And radio waves are the ones with the longest wavelength that you can see, they can be the size of 1 kilometer, and that's the ones that we use for radios. And actually, that's pretty much it. So remember, these are all the different types of light waves, but the only ones we can see are here in the visible spectrum. However, all of them travel at the speed of light because, as I told you, it doesn't matter which wavelength, the speed of transmission of the waves of electromagnetic waves is always the same. One more thing that I forgot to tell you is that electromagnetic waves, so light, are transverse waves. What does that mean? Well, remember that we had longitudinal waves, so where the perturbation was transmitted parallel to the wave, right? So imagine, for example, sound. Sound is a push that goes this way, and the wave is also moving this way, so we have a longitudinal wave. Well, in the case of the electromagnetic waves, the perturbation is a change in the electromagnetic field. And this change, and I know this is really hard to imagine, is perpendicular to the propagation of the wave. So the wave is going this way, and the electromagnetic wave field is oscillating either up and down, or, like this way and this way. And you need to imagine that this is perpendicular to this. And this always happens with electromagnetic waves. Long story short, just remember electromagnetic waves are transverse waves. Right, so you probably know that if you look into a mirror, then on the other side appears what seems to be you. And, of course, you probably don't find this shocking anymore, but you should, because how is it possible that you see an image of yourself that seems to come from a place where there's a wall? And in order to understand this, we need to think about what happens to light when it reaches the mirror and then bounces back. So, well, let's think about it, right? Imagine that this point here is giving off some light, right? So the light is really going in every possible direction. It's going like this, like this, like this, right? It's going doing all kinds of things. Now, however, we're not interested in what happens to all these light rays that go in all directions, because we know what happens. They are used by other people to see you, and they're like, oh, look, a hair. But we are interested in what happens to the rays of light that actually go and bounce off the mirror. Okay, so let's try to see what happens. Well, first I'm going to focus on this ray of light. And I'm going to assume that rays of light behave kind of like balls, right? So if I bounce a ball off the wall, what it's going to do is it's going to bounce off at exactly the same angle. So let's see if this could explain the fact that I'm seeing a guy over here. Okay, so what I do is I continue to draw this. Okay, well that's a terrible drawing, but you get the idea. Yeah, so this keeps going this way, and then it bounces off at the same angle. So in order to make sure that I'm drawing this correctly, I'm going to make a little line here. And I need this angle to be the same as this angle. And you may be wondering why on earth I'm measuring angles against this imaginary line and not against this. And the reason is really that this is 2D, right? So this angle could be this, but it could also be going into you, and it would be actually much bigger. So the way that physicists deal with this is that every time we're talking about angles against surfaces, we draw this perpendicular line to the surface, and every single angle is measured against this line. This line is called the normal, because normal just means perpendicular. So anyway, this guy bounces this way and then goes back. So far, I don't seem to see anyone over here. So that's not going very well. So I'm going to try a different line, right? I'm going to try one that just goes this way and then just bounces back. So this goes this way and then bounces back. Okay, so now I have two lines. This one does this one does this. And I'm like, well, I still don't see a guy over here. But then I think, okay, well, imagine that I'm some guy looking at things from over there. I don't know whether this ray is coming from this guy or from somewhere over here, because this ray is actually seeming to come from somewhere behind the wall. Granted, it doesn't come from behind the wall, it has bounced from here, but it looks as if I don't know that there's a mirror here, I would just assume that this just came from somewhere over there, right? So what I can do is I can extend this ray in the path that if I was here, I would imagine this would have, right? So I would say, okay, well, this ray seems to be coming from somewhere there, right? And now we start to see, let's see if this thing does the same thing. So I can also extend this right here, that it looks like it's coming from over here. And now we see that these two imaginary light rays converge precisely at the same point, but at the back of the mirror. And that's an explanation for what's going on. What's going on is that light rays bounce in such a way that they look like they're coming from some point behind the mirror. And if I want to find this point, all I need to do is apply this law. I draw a bunch of rays coming out of the point that I want to find the image of. Then once I have the ray drawn, I make sure that the angle at which it bounces back is the same as the angle at which it came in. So this angle should be the same as this angle. And then all I need to do is to draw the prolongation of these lines until they meet each other, and they will always meet at a point that's the reflection of the one they were coming from. That's pretty much it. So we can explain the fact that there's images behind mirrors simply by assuming that light rays behave like balls, and they just bounce back at the same angle that they bounce in. Neat. Alright, so now for something a little bit more complicated. I'm sure that you're familiar with this picture where you put a pencil in a cup and then the image looks distorted. And obviously this must have something to do with how light is propagating inside this cup. Now what we would like to do is to find out exactly what about light propagation in here makes this image appear the way it does. In order to do this, the easiest thing is to use a laser to shine through, for example, a piece of glass and see what it's doing, to see if we can work out what's going on with the light when it changes medium. So for example, when it goes from air to glass or something like that. All right, so let's take a look at that. All right, so this is an image that I got from Wikipedia where a beam of light is shown through a glass, and as you can see, it bends. And well, that's quite shocking, right? Why would it bend? What in the glass would make this thing bend? I mean, isn't it transparent? Shouldn't this just go through? But no, apparently it bends, and then it comes out exactly at the same angle that it came in, as you can see. See, these two things are parallel, but here inside it's bent. So it would make sense then that if I'm looking at things from here, so here's my eye, I really would see an object placed in here a little bit higher up, right? Because this thing has moved up. And this is the same thing that happens with a pencil. We can see it displaced a little bit, and that's apparently because light is bending inside the water or inside the glass. Now, there is a reason why this happened, and this is what I'm going to show you right now. So in order to understand this, what we need to do is take a look at what happens to the wave fronts of this light, and especially at what happens to the speed of light once it reaches the glass. So light is a little weird, right? Because it's a wave that propagates through vacuum. And you know that sound, for example, does not propagate through vacuum because it needs molecules to go through. So the more molecules you have, the faster it goes. But light is kind of the opposite, right? It goes through vacuum, and actually when it runs into molecules, it slows down. It slows down because it has to kind of walk around the molecules. Actually, what's really happening is related to something called photons and the fact that they get absorbed and re-emitted in here in random ways, and then things go slower. But never mind that. You can imagine simply that this a wave that's going in here, and then because there's so many obstacles inside, it just goes a little slower when it reaches the glass. And you'll be thinking, okay, so what does speed have to do with bending, right? Why would something that goes slower bend? Like when I start going slower, I don't bend, I just keep going straight. And in order to understand this, we need to draw a ray diagram. So let me draw this ray diagram. So imagine that this is, so after this we have glass, and in glass light is slow, and in here we have air, and in air light is fast. Okay. Now remember that we can depict a wave through wavefronts. Just like waves in the sea, remember, so in a wave in the sea you have something like this, right? And the line that unites all the crests of the wave, that's called the wavefront. So we can do the same with light. And what I'm going to do is I'm going to draw several waves that are coming in here at an angle. So I'm going to start here so that I don't mess up this drawing. Okay, so here's some light that's coming in this way at this angle. And of course, we could draw the ray, and the ray, which is what we saw up there, is coming in this way. So now we ask ourselves, okay, well, so here are my wavefronts. What happens once the light enters the glass? Well, what happens is that here, these wavefronts are traveling very fast, right? So let's say in 10 seconds they travel this much, right? But here, they're not going to travel as fast. They're actually going to travel much less, right? They're going to travel, I don't know, let's say this much. Because in the glass, light is slow. So, for example, this point here will only travel until here. But this point here will actually travel all these because it's faster. So now if I join these 2 points in order to make the wavefront like this, let's see what happens. So here's the 2 points joined, and lo and behold, this thing is bent, right? If I draw a ray now through here, I can see that the light has bent. And the reason for this is simply that when the wavefronts come in, part of the wave is going slower, part of the wave is going faster, and therefore the wavefront bends, and then we can see the ray bending like this. This phenomenon is called refraction, and I put that up there, but I'm going to write it again, refraction. And it's the reason why light bends when it changes medium. Now what would happen, for example, if the light was going from glass to air? Well, exactly the same, but opposite, right? It would be doing this. So in this case, instead of having a smaller angle, it would have a greater angle, because again, this part would be traveling very little, but this one would be traveling faster, and then things would bend this way. So it would do this. So now we are in a position to go back to our glass that we had before and try to understand what's going on. Right, so I could, for example, draw the wavefronts here, and here would be my wavefronts. And then what happened here is that while this guy traveled very little, this guy traveled a lot, and then the wavefronts became like this. And then when this hit this guy traveled a lot, this guy traveled little, and then the wavefronts become like this. And we can explain why light bends in glass, which is awesome. But we're doing physics, we're not doing art or some soft science, which means that we're not happy with knowing just that light bends. You know, that's not very good for a physicist. We actually need to know how much light bends. And in order to do this, we're going to need mathematics, as always. So if you don't like mathematics, brace yourself. Now, the first thing that we need to know is that we need to quantify this idea that light travels slower in some places and faster in some places. And in order to do this, we need to think about the speed of light. We would like to have a number that told us how much slower light is traveling here than here, so that we could then relate this difference in speeds to the angle that it bends. Now for this thing, we're going to need something called the refractive index, that we write as n. So n is called the refractive index. So refractive index. And n tells us how much faster light travels in vacuum than in our medium. So it's always bigger than 1 because nothing travels faster than light in vacuum. So let's just define this then. N equals the speed of light in vacuum divided by the speed of light in my medium, for example in glass. So imagine that the speed of light in glass is half of that in vacuum. Then n equals 2, because this divided by this is 2. Imagine that the speed of light is 1.5 slower in vacuum. Then this will be 1.5, and so on. So the idea is that the bigger that n is, the slower the light travels in that medium. So if I have an n of 30, means that light travels 30 times slower in that medium than in vacuum. Normally, n in a glass is around 1.5. So if this is a glass, it will have an n of around 1.5. And n in air is pretty much the same as in vacuum. So light travels at the same speed in vacuum and in air, and n is equal to 1, more or less. Okay, it's not exactly equal to 1, but close enough for all intents and purposes. So now what we would like to know is, okay, so here I have two mediums, one with n equals 1, one with n equals 1.5, and I'm going to have some ray of light coming in here. So let's draw it. Here's my ray of light that's coming in. And we know that it's going to bend somehow. And we know that it's going to bend like this, because remember, light travels lower here, which means that this part of the wavefront travels less, this one travels more, so the bending is from more to less. Good. So what we would like to know is the relationship between these two angles. The first thing that we need to consider is which angle are we going to use. Now, you would be tempted to think that this is the right angle to use, but the problem with surfaces is that they're two-dimensional, so this is a very ambiguous definition, because this could go like here, here. So we don't use this angle at all. Instead of using this angle, we use this angle, with this line here that we call the normal. Normal just means perpendicular. So this is a surface, we make a line that's perpendicular to the surface, and all angles that we measure, and this is the same for reflection measured against the normal. So let's do that. So here's the angle and the other angle. Now this angle, we call it the angle of incidence. Theta stands for angle and I for incidence. So let's just write that down. Angle of incidence. And because what happens here is refraction, we call this angle the angle of refraction, or theta r. So angle of refraction. Okay, so what we would like to know is the relationship between this guy and this guy if we know this and this. Now, because we don't necessarily have to have air and glass, let's just call these ones N1 and N2. Simply because, well, here we could have, I don't know, water and honey, for example, and this would still work. Now, I'm not going to prove this to you. If you do the IB, I will prove this to you. But imagine that this is just an experimental result, something that you can figure out after looking at many angles and doing many experiments, and then you will find out that there is a mathematical relationship between these two things, and it's the one that I'm about to show you. This relationship was discovered by Snell. That's why it's called Snell's law. Though I think some Arabian mathematician found it way before him, or at least was onto something. So anyway, what he discovered is that if you multiply N1 times the sine of the incidence angle, you get the same as if you multiply N2 times the sine of the angle of refraction. And I know that this has a lot of weird symbols and it has signs which people hate, and so you're probably not gonna like this. But that's the law that this thing follows. So just because this is a little strange, let's actually try and use this for one example. Okay, so imagine, again, I have air here, so n equals 1, and here I have glass, n equals 1.5. And let's imagine that I know that the angle of incidence is, I don't know, let's say 50 degrees. So we would like to find out what this angle is. Let's see how we do that. Alright, so like with any formula, the first thing that we do is to see which numbers we have and plug them in. Okay, so let's see, do we have n1? Yes, n1 equals 1. Good, so 1 times, now sine of theta of incidence. Do we have this angle? Yes, it's 50 degrees, so sine of 50. Now, remember that this is just something that you plug into your calculator and it's going to give you a number. So in your calculator there's this key that says sine, and you just plug it in and then it gives you a number. So there's nothing to worry about. This is not done by you, it's done by your calculator. Okay, so this has to equal N2, which is 1.5 because it's glass. So 1.5, and then times the sine of the angle of refraction, which we don't have. That's what they're asking us. Okay, so we have an equation with one unknown. So what I'm going to do is I'm going to isolate first the sine of the angle of refraction, and then I'm going to find out the angle through the inverse sine, which again is a function that is in your calculator. So let's try to do that. Alright, so first thing, I'm going to calculate this thing and turn it into a number, but before I do that, I'm going to flip this around because people get confused when the unknown is on the left. So I'm just going to say 1.5 sine theta refraction equals 1 times sine of 50. Okay? So basically we're trying to find this out. Good. Now let's calculate this thing, which is just a number. Now sine of 50 equals 0.77, and 1 times 0.77, that's just 0.77. So we've got 1.5 times sine of theta r equals 0.77. Now remember, I want to get rid of this thing which is multiplying, so I need to divide both sides by 1.5. So let's just divide by 1.5 here, and then divide by 1.5 here, and then of course this will get crossed out. So then I get sine of theta r equals 0.77 divided by 1.5, and that gives me 0.51. So 0.51. And now I need to find theta r. In order to find theta r, all I need to do is to go to the calculator and write sine minus 1 of 0.51. So I'm going to write here theta r equals sine minus 1, and this does the opposite of the sine. So if 0.51 is the sine of something, then this will give you the angle. So again, we plug this in our calculator and we get, so sine minus 1 of 0.51, 30.7 degrees. And that's it. We found the angle of refraction. Make sure that you understand this process very well, because you're going to be doing this over and over and over again during the class. Now that we know about refraction, we can start looking at some even more bizarre stuff. So for example, here's a piece of glass, and this is a laser that's being shown on this glass. And as you can see, the light never comes out, right? So they should go out, right, according to what we just studied with some angle. But it just goes in and then never comes out, just stays inside the glass, keeps bouncing back. And we may wonder, why does this happen? Shouldn't this be coming out? Isn't this glass, isn't this transparent? But actually this phenomenon can be very easily explained with what we just learned, which was Snell's law. So let's take a look at what's happening here. So in order to do this, we need to make a little drawing and then try to figure out why this thing is not coming out. Okay, so here we've got some glass, right? So, and then there's this laser. Now it comes in just fine, but the problem is when it bounces here, right? So basically what we've got is incoming ray this way, and then there's no outcoming ray, but there should be one, right? So let's just draw it anyway. It should go like this. And remember that both angles are measured against the normal. So this is slow, so it's going from glass, which is slow, to air, where it's fast, right? And now, I don't know if you guys remember, but what happens when things go from slow to fast is that the angle gets bigger. Because remember, here's a wavefront, so this part moves more than this. So this thing bends this way. So this may make us think, right? So, okay, in theory, when I have a light ray, let's just draw another one that's coming in this way. It's just going to bend a little bit like that, right? And a little bit more than it was bent before. As I keep making this bigger, this will always be bigger than this angle. But this means then that I can never get to 90, because this angle would always be bigger. So it would be here, which would be like coming back into the glass. And in fact, there will be a certain angle here for which this angle will be exactly 90. Right? So let's see if I can find a different color. So there will be this angle for which this will never come out, but actually just come this way at 90 degrees. So again, there's this angle, and I'm going to call this a critical angle, for which this thing does not come out. And if it does not come out, this means that everything that goes here bounces back. Now, how are we going to find this critical angle? Well, easy. We just need to use Snell's law. So we have that n1 sine theta 1, just like before, theta incident, sorry, equals n2 sine of theta refraction. Okay. But now we know that the angle of refraction, we want it to be 90 degrees, which is when this thing never comes out. So this is going to be 90 degrees. And this thing is going to be the critical angle, which is the angle of incidence. So let's do that. This, in this case, is going to be the glass, because it's going from glass to air. And this thing is going to be 1 because it's air. Okay, so let's do this. So we got 1.5 times sine of the critical angle is going to equal n2, which is 1, times sine of 90, which is 1. So this is going to equal 1. And from here we get that the sine of the critical angle has to be equal to 1 over 1.5. And therefore the critical angle, remember, is the sine minus 1 of this thing, and we can calculate it to be 41.8 degrees. So 41.8 degrees. This means that for any angle that this laser goes in that's bigger than 41.8 degrees, things are going to bounce back. And that's what's happening here, right? You can see that this angle here is bigger than 41.8 degrees, therefore nothing comes out. So it bounces back. And this angle is still bigger than 41.8 degrees, so it just bounces back. But once it reaches here, this angle is smaller than 41.8 degrees, so the laser just comes out of the glass. And this is extremely useful for all kinds of things, for example, telecommunications, and I'll show you that in a second. But before we do this, I would like you to think for a moment, do you think it would be possible to have a critical angle for a light that's going from air to glass? Think about it for a while, pause the video, and say it out loud. Okay, well, hopefully you got your answer. What really happens is that because this angle is always bigger than this one, it's impossible to have a critical angle from air to glass. So things coming in from air to glass, they will always go through. This will only happen when light is going from a slower medium to a faster medium. So from glass to air, from water to air, from anything to air, you will have a critical angle. From air to anything, there's no critical angle. Everything gets through. One more thing. This phenomenon is called total internal reflection. And the reason for this is just that everything is reflected, right? So that's hence the word total, internal because it's inside, and reflection because everything is reflected. And this is a very important property of light that we can use to transmit data through wires. Let me show you how. All right, so this here is called a fiber optic cable. Now, as you can see, this is just a little wire made of glass. And there's light coming out of here, but there's no light coming out of the sides. And the reason why there's no light coming out of the sides is precisely because of the critical angle. Right? So we have a little wire like this. Then light is coming in, and it's bouncing and bouncing and bouncing. But because this angle is always bigger than the critical angle, then nothing comes out. Until, of course, the very end. Because when it reaches this place, then this angle is smaller than the critical angle. So I say, why would I want to get light, inside a cable to not come out? Well, actually, because I can use this to transmit information. And there's a very high chance that the internet at your home works thanks to this. Thanks to this remarkable property of light, you can transmit lots and lots and lots of data simply by transmitting light through these really long wires. Because it's light, it goes really, really fast, and you can just transmit a buckload of data. And not only this, but this has almost no friction, so no energy loss, like in an electricity cable, things like that. So this is a very useful technology in order to transmit data for your internet, for example. But not only for this. So I can bundle this up, for example, and put it in a cable, and put it inside your stomach. And then I can look inside your stomach and see, I don't know, if there's something wrong with it. So this is also ideal for transmitting images for mini cameras that I can put inside your body, and then doctors can see what's wrong with you. So this pretty simple idea of total internal reflection actually has lots of important applications in technology that you use every day. Okay, so we've come to the end of this very long video, and I apologize for that, guys, but well, this is one of the hardest things that we're doing this year. Let's see if we've done everything that we had to do. First thing, describe the formation and characteristics of an optical image seen in a plane mirror. Yes, we did that. And remember, you just draw your little mirror, and all you need to do is to make sure that the angle of incidence is equal to the angle of reflection, and then you just make this one longer, and then you see where they meet, and then that's the image. Okay, use the law of refraction, we did that. Use the ray diagrams to show the path of refracted rays, we just did that. Say the meaning of the critical angle, hopefully you understood that. And finally, identify and describe internal and total internal reflection using ray diagrams, which is what we just did. Alright guys, well, I'll leave you with this, and good luck with the problems. It's not going to be easy, but hopefully it's going to be fun. See you guys later.